Okay. First of all, literally, this means, in my case, let's say it's, I'll just rewrite these with some numbers. Okay, so first one might be 5x to the 7th squared, okay? Now, literally, I mean, there are rules for the exponents. You know, you're going to square the 5 and you're going to get 25, right? And then you're going to take x to the 7th squared, which would be x to the 7th times x to the 7th, which would be x to the 14th. When you do a power of a power, you multiply the exponents. So let's make sure we understand why. Okay, so one way of writing this out is just 5x to the 7th, 5x to the 7th, right? Now, you wouldn't want to do this if this was the 30th power. You wouldn't want to write out 30 of these, just to illustrate the rule. This is just straight multiplication, so you can rearrange it. 5 times 5 times x to the 7th times x to the 7th. Right? And you can write this out, debating about whether I really want to. Should we use a smaller exponent for the x? But I'll just note up here that x to the 7th and x to the 7th is the 7th, right there. I wrote it all out. That's what x to the 7th means. And of course, that's x to the 14th, because you got 14 of them, right? And again, I recommend strongly for your future happiness and security that you obviously you're not going to write that out, but think it. Remind yourself of why we're adding these exponents. Because you add how many you got here to how many you got here, it gives you how many you got. And then you can express that in terms of an exponent. So I urge you to do that. But that's then 25 x to the 7 plus 7. You got 7 of these and 7 of these. This is 25 x to the 14. Now you summarize all that in the rule. And if you remember the rule, that's great. Okay. But you do want to remember why the rule is what it is. So alternatively, it's 5 squared times x to the 7 squared. And you want to understand it this way too. It's 5 squared because, of course, you write out this way, you get a 5 here and a 5 here. Okay? Whatever this power is, that's how many 5s you're going to end up with. And that's then 25 x to the 7 times 2. 25 x to the 14. Okay? Try to understand it both ways. Try to visualize it both ways, even if you add x to the 38th to the 50th power. Well, what's that mean? You got 38 x's, and you got to do that 50 times. Okay? Okay, well, over here, now we got our fractional expression, and let's say this is 8 x squared y to the 5th over, well, that was 11 x to the 5th y raised to the 6th power. Those numbers come out. Okay. Well, I'm not going to write all this out, but you kind of want to visualize. You know, you're going to have 6 of these, which is going to give you 6 8s and 6 x squared and 6 y to 5th, right? And by 6x, or 6 y to the 5th, let's say, that means again 5 y's 6 times. Writing it out like this, you can visualize that. Only a crazy person would always write these out. If you want to be that crazy, okay, you know, we're not crazy. To an extent. Okay, well, anyhow, you get them. 8 to the 6. X squared to the 6. Y to the 5th to the 6. Divided by 11 to the 6. So of course you multiply the denominators. You're going to multiply this thing out, 6 of them. You're going to get 6 of these in a row. So it's going to give you 6 11s and x to the 5th. They're going to be 6 of them. And a y, they're going to be 6 of them. Okay. Now, I would do 8 to the 6th, which is 2 to the 18th, which is about 280,000 maybe. Little question mark on that number, something in that vicinity. Give or take a couple of 10,000. Times. I'm going to write it out. I'm going to write out the rule. And again, I'm going to remind myself of why it's 2 times 6. Because you got x times x written 6 times. That's going to give you 2 for each of the 6 times and all that. So we're kind of visualizing this. Over 11 to the 6. That don't make me do 11 to the 6. Okay. That's like a million, but then you get use binomial expansion. 10 plus 1 to the 6 is approximately a million plus, I'm going to say 1,700,000 or something like that. And I could be way off that when you get bigger powers. What do you got? Let's see. Oh, geez, I like that. Okay. And then that's x to the 5 times 6, y to the 6. So that's something like 280,000 over 1.7 billion, which is like, oh, come on. I'm just going to write out the numbers right now. I can reduce and I can divide all this stuff out. It's like 28 over 170, okay, which is like point. Goes in 0.15. I would just say, okay, maybe it's 0.15. Just to take a wild guess. Okay. And then times x to the 12, y to the 30th, over x to the 30th, y to the 6th. And of course, now we can reduce this, right? That's where we want to really start. If we want to talk about negative exponents, positive exponents, okay? And somebody, as I say, wrote some of this out with negative exponents. So let's look at what we can learn from this expression. Okay. And let's see, point 15. Might be a 0.16, even 0.17, a little more 0.15. Okay. So let's look at this expression. And I'm gonna change my estimate. I'm gonna go with 0.16, 0.17 wouldn't surprise me. Good. I don't know, maybe I got a good night's sleep last night, or mostly I'm just lucky. Okay, 0.16. Then you got x to the 12th, y to the 30th, over x to the 30th, y to the 6th. Now, open math is going to tell you to cross things out and stuff like that. I want to use the rules. I don't like crossing things out because it gets misapplied. But in a case like this, it is safe. Still, okay, well, make a couple of notes here. Okay, first of all, means you got 12 x's in a row, right? And then you got, make this look a little longer. You have 30 of these, okay? Now, using what you know about fractions, it means you could do I'm just going to write 12 there to indicate that there are 12 of them. I don't want to keep writing times down because of time. I can take 12 of these and put them under here so that that's just going to be like 1, right? Because it's the same thing divided by itself. Which one is divided by itself. And what's that leave us? It leaves us 1 over here. And how many of these are there? 18, right? Because there were 30 and I put 12 of them here. Well, that doesn't take too much thought. Okay. And that, of course, equals just 1 over 18 of them, which is 1 over x to the 18th. And that's the reason you could subtract the 12 from the 30. Okay. And you could get 16 times 1 over x to the 18th. Okay. And you can do the same thing with the y's. You're going to have a string of 30 y's here, a string of 6 y's here. You can match 6 of these up with these. Gives you 1 and leaves you 24 of them, right? So that's it times y to the 24th. And you get this. Okay. Now, another way of writing that out. We just subtract the 6 y's that we have down here from the 30 y's we have up here. It'll leave us 24 of them. And we got a question, so let's deal with that. And also, I noticed that my board isn't in the right position. We'll fix that in a minute. Stop. Now, we did have one person who made an acute observation, just left these numbers the way they are, okay? And said that they don't reduce. I said, did you do the prime factorization? Yes. Okay, that's what you'd officially do. Of course, you can look at these numbers and see that all you got up here is powers of 2, right? 8 is 2 to the 3rd power, and you got the 6th power of that, so you've actually got the 18th power of 2. So this is just a bunch of 2's multiplied together. That's what this number would be if you did it accurately. And this number is a bunch of 11s multiplied together. Well, 2s and 11s don't have any factors in common. Okay. In other words, if it's a bunch of 2s, it's not divisible by 11. If it's a bunch of 11s, it's not divisible by 2. So that's absolutely right. This number wouldn't reduce. Now, I went ahead and estimated it, just to make sense of it. Okay, but normally I want you to leave the number the way it is, and ideally reduce it. And if it's a reasonable number in the hundreds or something like that, we can easily do that. Get numbers up into the hundreds of thousands and millions. Not that much harder. But that's just a side comment. We're not really going to worry about that now. We're trying to focus on these exponents. So what we say is, again, where did I get that y to the 24th? It says that I've got a string of 30 y's up here and 6 y's down here. I can take 6 of these, match them up with these 6, leaving me 24 of them. Much along the lines of what I did here. And this was off the screen, so let me quickly. You know, x of 12th over x of 30th means you got 12 x's and you got 30 x's. I can take 12 of the x's down here and match them up with this, and that just gives me 1. Okay. Then I've got the other 18 x's. I've got to have them all in the denominator, but I've got 18 of them. And this gives me 1 over 18, product of 18 x's, right? Which is x to the 18. Okay, that's the reason the rule works. Once we understand the reason and can visualize it, we can visualize why we get y to the 24th here. Because again, just like I matched up these 12 product of 12 x factors, we could match up 6 of these, 6 of these. Okay, so we get y to 30 minus 6 over x to the 30 minus 12. You see from here why we got the 30 minus 12, because we got 30 of these matched up 12, leaving us 18. So this is the way the rule works. One way the rule works. Okay, so there are a couple of ways we can write this out. Find the rule looks like this. And hopefully this isn't confusing. And what we really get to now is we can do this another way. Okay. I'm just going to do x to the 12th, y to the 30th. Over x to the 30th, y to the 6th equal. I could say, well, you know, if I can subtract the 6 from the 30 here, then I should be able to subtract the 30 from the 12 here. So just like I subtracted 6 from 30, which gave me 24, if I subtract 30 from 12, I'm going to get x to the 12 minus 30, y to the 30 minus 6. Now 12 minus 30 is a negative number, so you can't really visualize it like this. But the rule works because of this. If the rule is going to be consistent, you should be able to subtract the larger from the smaller. We could write this as x to the negative 18th, y to the 24th. But it's also equal to y to the 24th over x to the 18th, right? So we conclude that x to the negative 18th is 1 over x to the 18th. Okay. So now we can subtract whether we're subtracting a bigger number from a smaller or smaller from a bigger. Sometimes this form is more appropriate to what you want to look at, depending on what you're doing with these symbols. And sometimes this form is more appropriate. If it's in this form, we say write it with positive exponents, because all my exponents are positive. Okay. In this form, we say write it without denominator. Okay. There's no denominator in this, but I have to use a negative exponent. Okay. So this is a form with no denominators. And this is the form with only positive exponents. Make sense? Okay, it's not particularly difficult. Let me give you a couple to do. Just see if you have this. So let's try. I'll give you numbers if you don't have to translate. I'm trying to write through is a 5. That's the fifth there in case that's mostly hard to read. Okay. So what we're going to do is write this both ways. Write it with no denominators. Write it with only positive exponents. Okay, so things are a little jumbled here. Might be a little hard to sort it all out, but the logic of what we did was up here in terms of grouping x's in this case to give us a 1 and then writing out whatever we got left over. We see that this is 0.16 y to the 24th over x to the 18th, right? We also see that if we use the idea that you could subtract whatever's in the denominator, subtract the exponent of the denominator from the exponent of the numerator, then we're going to get x to the negative 18th y to the 24th. Okay. And logically, if we can get y to the 24th by subtracting the power 6 from the power 30, right? So if we can subtract powers on the y, we should be able to subtract powers on the x. If we subtract powers on the x, we get x to the negative 18th. Now, it's the same expression. We know that this divided by this equals this because we worked that out up here. Up here we had the 0.16 on it. That wasn't even totally accurate. Okay? So these two expressions have to be the same. Well, y to the 24th is the same, but one of them has x to the negative 18th, where the other has x to the 18th in the denominator. We conclude that x to the negative 18th is 1 over x to the 18th. And that's why we say that, I'm going to write this out. Here's the rule of exponents. This is the whole topic of the next set of problems, okay? Next assignment. Okay. Now, this A and this B are not your A and B. They're just the symbols A and B. If we don't have the backward apostrophes in front of them, they're just symbols. They're not numbers. They don't stand for your personal numbers. Okay, so this just means whatever A and B are, A to the negative B equals 1 over A to the B. Of course, that works for your personal numbers, okay? But it works for any numbers. Any number to the negative power is 1 over that number to the positive power, okay? And that's the whole topic. We want to be able to do this, and we want to be able to express things like this in this form with no denominators, or in this form with no negative exponents. Okay? We have to understand that they're equivalent. So you're going to get exercises. That open math is going to give you some explanation on it as well if you need it. Okay? If you're already familiar with it from earlier coursework, great. You probably don't even need to really watch the open math videos. Or you don't need to go back and look at my video, okay? I mean, the one I'm posting, I'm recording right now. Whatever allows you to work the problems is going to work, okay? Now, another thing that I need to keep repeating is, remember, working the problems with all the information in front of you and all the help is not the same as working the problems. It's a step in learning to work the problems, right? To learn how to work the problems, you really should be going back on these assignments a couple days later and working through them without anything. And if you need something, then you go ahead and use it, but then a couple days later, go ahead and work them. That really gets it into your head, okay? Also, I advocate if there's stuff that you think would be beneficial to you in my video or in an open math video, click through it, find the part that you really want to look at, or just click through it to remind yourself of what you're being told and relate it to what you did when you did the problems. That's how you learn the stuff. Okay. Okay, let me pause for a second and see how much more I need to say, and then I'll give you some more problems to work. Okay, so let's work through these. This means then x squared to the fifth, y to the fourth to the fifth. This means x to the fourth to the third times y to the third. You want to write it out really carefully to be sure that you're tracing all your steps. In case you make a mistake, you want to write out the step. Now, if you're getting it right without this step, and a lot of you are, be careful, right? Skip steps, make sure you're very careful when you do it. And x squared to the fifth is x to the 2 times 5. Y to the fourth to the fifth is y to the 4 times 5. Reinforcing the rule. Good idea. So writing it out in detail, this is what we have. And then that gives us x to the 10th, y to the 20th, over x to the 12th, y cubed. So depending on how you want to write it, if you just do power the numerator minus power the denominator, this is going to be x to 10 minus 12, y to the 20 minus 3, which is x to the negative 2, y to the 17. to the x to the third. And if you're moving along and you're doing a lot of these, it's real easy to miss something like that. Okay, so we have x to the third times, I won't write out all the details. Partly because I just don't have enough room on the board, okay? I don't want to crap things up too much, but I think everybody understands why this is x to the 6, y to the 9. And then x to the 12, y to the 12. Okay, well, that is, well, x to the third times x to the 6, you know perfectly well, is x to the 9th. You got x to the 9th, y to the 9th, over x to the 12th, y to the 12th, which is x to the 9 minus 12, y to the 9 minus 12, which is x to the negative 3, y to the negative 3, or 1 over x cubed times 1 over y cubed, and that's x cubed and root square. Okay. That's 1 over x cubed, that's 1 over y cubed, and that's just like the rule that I wrote down somewhere. Move, that's not just like a to the negative b equals 1 over a to the b, and remember that's true because at least made very plausible by what we did over here. I try to understand that development. Above all, make sure you got the rule correct. And of course, then this could be just written as 1 over x cubed, y cubed. And I don't see people having a lot of trouble with this, okay? You know, do little mistakes in bookkeeping and stuff like that. Well, after you make a couple of mistakes, you start avoiding that, right? So if you do practice and everything, then you're going to be good. Okay, well, this is x squared z cubed and negative 3 divided by x z squared to the negative 3. In other words, numerator to the negative 3, denominator to the negative 3. Of course, the denominator has a power. Okay. So we could write the numerator, of course, that's going to be x to the negative 6, z to the negative 9. The denominator, we have a couple of choices. We can work inside the parentheses, or we could apply the rules for power. Here, I'm going to apply the rule for power, but most of you will choose to work in parentheses. You're going to get it right either way. But just to demonstrate, you understand that we could write this as x z squared to the negative 6 because we have the negative 3 power of the second power, right? So we'll find these two powers gives us a negative 6 there. Most of you probably got x squared z to the 4th to the negative 3. Well, it comes out the same. It's really your choice of which order and which order you multiply the powers. Okay, so we have x to the negative 6, z to the negative 9, over x to the negative 6, z to the negative 12. So that's, if you just subtract exponents, you get x to the negative 6 minus negative 6. Z to the negative 9 minus negative 12. Okay. Now, most of you seem to have gotten z to the negative 21st. But if you're really careful about writing this out, you have a negative, well, you're subtracting the negative 12, right? You got to have a couple of negatives there. You're going to get a z to the 3rd, okay? And I didn't even pick up on that when I was looking at the paper, okay? So I'd have called you on it if I'd have seen it, but I didn't even see it. Well, a couple of things here now. Well, that's one of them. Be careful. When you're subtracting exponents and you subtract the negative exponent, you better have those two negatives there, which will give you a positive point. So this equals x to the negative 6 plus 6, z to the negative 9 plus 12, equals x to the 0, z to the third. Okay. Now, it's like I said, if you got that z to the 21st in the denominator, which I think most of you did, I wasn't looking that closely. And again, it's just you, just one of your negative signs. So it's, you're following the rules. That's what I want to see. And then it's like I said on bookkeeping, you know, it's like raising this x to the third here to the third. Easy to do that. So you got to be real careful, which is why you write things out in a lot of detail when you're first doing it. And make sure all the symbols in the right place. But it's not a major error, it's just, you know, little bit of brain freeze, a little bit of not noticing. It happens to everybody. Okay, now let's see what do we mean by x to the 0? Well, what in rules of exponents is that x to the 0 is 1. It's just a rule, but there's a reason for it that I'll explain after we get through this. That's 1 z to the third, which is z to the third. One reason x to the 0 has to be 1, of course, is that we have x to the negative 6 divided by x to the negative 6. What's x to the negative 6 divided by x to the negative 6? 1. So, but it's also x to the negative 6 divided by x to the negative 6 by the rules of exponents is x to the 0. Therefore, x to the 0 better be 1. Otherwise, our entire system of algebra comes crashing down around us, which would be more of a tragedy than you think. We had an interesting discussion about what 0 to the 0 is, okay? Comes out of the idea that x to the 0 is 1. Anything to the 0 is 1 is 0 to the 0, 1. Okay? And I talked about how you do a limiting process, and you can see that 0 to 0 could mean anything. Okay. So here we have this, and just real quickly, that's going to give you x to the negative 8, y to the 12, over x to the negative 2, y to the negative 4, to the negative 4. Now this time I worked out the denominator before I did the negative 4. It wouldn't make any difference, okay, if I did xy squared to the 8th. It's still going to come out x to the 8th, y to the 16th. So we got x to the negative 8, y to the 12 equals x to the negative 8 minus 8, y to the 12 minus 16, which is x to the negative 16, y to the negative 4, which is 1 over x to the 16. Okay. Check me out on that. But looking at it, I've got an x to the negative 8 here, x to the negative 2, and an x to the 8th here. And negative 8 minus 8 is minus 16. It's easy to see, you know, x to the negative 8 and x to the 8, and you want to say that's x to the 0, but it isn't. Write it out carefully to avoid that error. Okay. And then that's got to be y to the 12. That's y to the negative 4 to negative 4, which is y to the 16. So that's that. I think it's right. Okay. Well, I think we're in good shape. Work things carefully. And I didn't get to go over scientific notation. I'm going to let you puzzle on that. It's fairly straightforward, but if there's a problem on it, we'll address it next time.